Close your eyes for a moment and imagine a wide, quiet ocean at night. The surface is calm, almost completely still. There is no wind, no sound of waves breaking, only a slow, gentle movement beneath you. You are floating, not sinking, not swimming, just resting on the surface of the water. The sky above is dark and open and very far away. The ocean below is darker still. It stretches downward, far beyond what you can see. The deep ocean begins where light begins to fade. Not suddenly, but slowly, layer by layer. Scientists divide the ocean into zones, based on depth and light. These zones help us understand a place that is otherwise difficult to reach. The uppermost layer is called the epipelagic zone, often known as the sunlight zone. It extends from the surface down to about 200 meters. In this layer, sunlight is strong enough to support photosynthesis. Phytoplankton live here, tiny organisms that use sunlight to produce energy. They form the base of the ocean's food web. Almost all life in the ocean depends on them. Even the deepest creatures are connected to this thin layer above. As you float here, you are still within this zone. The water is relatively warm compared to the depths below. Sunlight can still reach you, even if it is faint at night. During the day, this layer would be filled with light, moving and shifting with the waves. But now, in the quiet of night, the surface feels softer, more still. Beneath you, the water begins to darken. The ocean is not a single empty space. It is structured, layered, and slowly changing with depth. Below the sunlight zone, light begins to weaken. Colors fade first. Reds disappear, then oranges, then yellows. Blue light travels the farthest, which is why the ocean appears blue from above. But even blue light has its limits. As depth increases, less and less light remains. This gradual loss of light marks the beginning of the deep ocean. The deep ocean is often defined as everything below 200 meters. This includes several zones, each with its own conditions. The mesopelagic zone, the bathypelagic zone, the abyssopelagic zone, and the hadal zone. Each one becomes darker, colder, and more pressurized than the last. Pressure increases steadily with depth. For every 10 meters you descend, pressure increases by about 1 atmosphere. At 200 meters, the pressure is already around 20 times greater than at the surface. This increase continues all the way down. Despite this, life still exists and adapts. The deep ocean is not empty. It is simply quiet. Temperature also changes with depth. Near the surface, water can be warm, especially in tropical regions. But as you move deeper, temperature drops. Below the surface layer, there is often a thermocline, a zone where temperature decreases rapidly with depth. Below this, the water becomes consistently cold, usually between 0 and 4 degrees Celsius. This cold remains stable, even across vast distances. The deep ocean is also defined by its stability, unlike the surface, which is influenced by weather, wind, and sunlight. The deeper layers change very slowly. Currents exist, but they move gently, often over long periods of time. Some deep ocean currents take hundreds or even thousands of years to complete their paths. This slow movement helps regulate Earth's climate. It distributes heat and stores carbon. The ocean is not just a place. It is part of a global system. As you continue to float, you may begin to sense the depth below you. Not visually, but conceptually. The average depth of the ocean is about 700 meters. That is far deeper than most mountains are tall. The deepest parts of the ocean, known as trenches, can reach nearly 11,000 meters. These depths are difficult to imagine. So instead of imagining the full distance, it is easier to imagine a slow descent, a gradual movement downward. With each meter, the environment changes slightly. Light fades, pressure increases, temperature drops. But it happens slowly, gently, without sudden shifts. The ocean covers about 71% of Earth's surface, and the deep ocean makes up the vast majority of that space. It is the largest habitat on the planet, yet it remains one of the least explored. Not because it is unreachable, but because it is difficult to access. The conditions require specialized equipment, strong materials, careful planning. Even then, exploration is slow and limited. This is why much of the deep ocean is still unknown. But unknown does not mean chaotic. The deep ocean follows physical laws, just like any other environment. Gravity, pressure, temperature, and chemistry all behave predictably. Over time, life has adapted to these conditions. Slowly, consistently, without urgency. The result is a system that is stable and continuous. As you rest on the surface, there is no need to go deeper yet. There is no need to rush. The ocean will remain here, steady, patient. You can simply observe and listen. The gentle movement of water beneath you, the quiet space above you, and the vast depth below. Slowly, gently, almost without noticing, you begin to drift just slightly lower as the surface world begins to fade. You are still close to the surface, but something is beginning to change. The water feels slightly heavier, slightly quieter. The surface above you is still there, but it no longer feels as close. Light still exists here, but it is softer now, more diffused. This is the upper part of the epipelagic zone, often called the sunlight zone. It extends from the surface down to about 200 meters. Within this layer, sunlight can still penetrate the water, but the intensity of that light decreases with depth. As light enters the ocean, it is scattered and absorbed. Water molecules absorb certain wavelengths of light more quickly than others. Red light is absorbed first, usually within the first few meters. Orange and yellow follow, disappearing gradually as depth increases. Blue light travels the farthest, which is why the ocean appears blue from above. But even blue light fades as the water becomes deeper and denser. As you drift slightly downward, colors begin to lose their clarity. Objects that might appear bright at the surface begin to look muted. Reds become dark, almost black. Yellows soften into pale tones. Blues remain, but even they begin to dim. The change is gradual, not sudden. There is no clear boundary, only a slow transition. The ocean shifts quietly from bright to dim, and from dim to dark. In this upper layer, life is abundant. Phytoplankton drift in the water, carried by gentle currents. These microscopic organisms use sunlight to perform photosynthesis. They convert carbon dioxide and water into energy, releasing oxygen as a byproduct. Much of the oxygen in Earth's atmosphere comes from these tiny organisms. Even though they are too small to see, they play a large role in sustaining life. Around them, small animals move slowly. Zooplankton drift and pulse through the water. Some move actively, others simply float. Many of them rise and fall in a daily cycle. This movement is known as vertical migration. At night, they move closer to the surface. During the day, they descend to deeper waters. This behavior helps them avoid predators, while still accessing food. Fish and other animals move through this layer as well. Some are fast, but many move gently. Their bodies are adapted to this environment. They rely on vision, because light is still available. Their eyes are often well developed, able to detect movement and contrast. This is a world where sight still matters. As you continue to drift, the surface becomes less defined. The movement of waves above you becomes softer. Sound behaves differently in water. It travels faster and over longer distances than in air. But here, there is little disturbance. The environment feels calm and consistent. Pressure increases as you descend. It does so steadily, without interruption. At 10 meters, pressure is about twice that of the surface. At 50 meters, it is about 6 times greater. At 100 meters, it is about 11 times greater. The increase continues with depth. But it does not feel sudden. It builds slowly. Temperature also begins to change. near the surface. Water temperature can vary depending on location and time of day. Sunlight warms the upper layer. But as you move downward, the influence of sunlight decreases. The water becomes cooler, more stable. This gradual cooling forms part of the thermocline, a zone where temperature drops more rapidly with depth. The thermocline is not always sharp. It can vary depending on region and season. In some places, it is clearly defined. In others, it is more gradual. But the overall pattern remains. Warmer water above, colder water below. As light continues to fade, the environment becomes less visually detailed. Shapes are still visible, but edges soften. Contrast decreases. The world becomes more uniform in tone. This is the beginning of a shift, not just in light, but in how organisms interact with their surroundings. Vision becomes less reliable. Other senses begin to play a larger role. Some animals begin to develop larger eyes to capture as much light as possible. Others begin to rely on sensitivity to movement, detecting vibrations in the water. These adaptations allow them to function even as light becomes limited. As you drift deeper still, the surface is now distant. It is no longer a clear boundary, but a faint brightness above. The water around you feels more enclosed, though there are no walls, only depth and distance. The sunlight zone is slowly coming to an end. At around 200 meters, sunlight becomes too weak to support photosynthesis. This marks an important transition. Beyond this point, energy from the sun no longer directly supports life. The ecosystem begins to rely on other sources. This boundary is not sharp. It is gradual. Light fades to a level where it is no longer useful for energy production. But it may still be visible for a short distance beyond. As you approach this depth, the environment becomes quieter still. Movement slows, and space feels wider. There is less activity, but not an absence of life. Only a change in how life exists. The last traces of sunlight linger above you, faint, distant, and slowly fading. Below you, the water deepens into a darker shade, a soft boundary between light and shadow. And as you continue to drift downward, the remaining light begins to dissolve into a dim blue twilight. The light above you is now very faint. It no longer feels like a source, only a memory of brightness. The water around you has shifted into a dim blue tone, soft and uniform. You are entering the mesopelagic zone, often called the twilight zone. It extends from about 200 meters down to around 1,000 meters. In this layer, sunlight is present, but very weak. It is not strong enough to support photosynthesis, but it still shapes the environment. The color of the water continues to change. blue light remains, but it is dim. Other colors have already disappeared. Red objects appear black. Orange and yellow lose their brightness. Everything becomes a shade of blue or gray. The further you descend, the less contrast there is. Shapes soften, edges blur. The environment feels quieter, not because sound is gone, but because there is less activity. Pressure continues to increase, steadily, without pause. At 200 meters, it is about 20 times greater than at the surface. At 500 meters, it reaches around 50 times greater. At 1,000 meters, it approaches 100 times greater. This pressure affects all living things here, but they are adapted to it over long periods of time. Temperature continues to decrease. The thermocline often extends through part of this zone. The water becomes colder, more stable, typically ranging between 5 and 10 degrees Celsius, though this can vary. There is less daily fluctuation, more consistency. In this dim environment, vision becomes limited. But it is not gone. Many animals here have large eyes, adapted to capture faint light. Some eyes are directed upward, to detect silhouettes above. Others are sensitive to very small changes in brightness. This helps them detect movement. At the same time, a different kind of light begins to appear. Not from the sun, but from living organisms. This is bioluminescence, the ability of organisms to produce light through chemical reactions. Bioluminescence is common in the twilight zone. Many species can produce light in controlled ways. The light is usually blue or green, because these wavelengths travel best in water. The chemical process involves molecules like luciferin reacting with oxygen, producing light without significant heat. These light signals serve different purposes. Some organisms use them to communicate. Others use them to attract prey. Some use them to avoid predators. One method is called counter-illumination, where an organism produces light on its underside, matching the faint light from above. This reduces its silhouette, making it harder to see. As you drift, you may begin to notice small points of light, appearing and fading. They are not constant, but brief. A soft flash, then darkness again. These are living signals, not reflections. Movement in this zone is often slow. Many organisms conserve energy. Food is less abundant than near the surface, so efficiency becomes important. Some animals drift, using minimal effort. Others move in short, controlled bursts. One of the most significant patterns here is vertical migration. Many organisms travel up and down the water column each day. At night, they rise toward the surface to feed. During the day, they return to deeper waters, to avoid predators. This movement happens on a large scale, involving billions of organisms. It is one of the largest daily migrations on Earth. Despite the reduced light, there is still structure here. Layers of organisms, distributed by depth. Some remain closer to 200 meters. Others stay deeper. These layers can shift over time, but they remain relatively stable. Sound continues to travel through the water, efficiently, and over long distances. Some marine animals rely on sound rather than sight, though this is more common in larger animals and deeper zones. The twilight zone is a transition between light-based and non-light-based environments. As you descend further, the remaining sunlight becomes even weaker. It is now barely visible, a faint glow above. The contrast between light and dark continues to shrink. Eventually, there is a depth where sunlight can no longer be detected by the human eye. This occurs before the end of the mesopelagic zone. Beyond this point, natural light from the sun is effectively gone. The environment becomes more uniform, more consistent. The sense of direction fades. Up and down feel less distinct. Only gradual change remains. Life continues here, but in quieter ways. Adaptations become more specialized. Energy use becomes more efficient. Movement becomes more deliberate. The twilight zone is not empty. It is simply subdued. A place where light is no longer dominant, but not entirely absent. And as you drift deeper still, even this faint blue light begins to disappear, leaving behind a deeper, more complete darkness. There is no longer any sunlight here. The faint blue glow has fully disappeared. The water around you is now completely dark, not dim, not shadowed, but entirely without natural light. You have entered the bathypelagic zone, often called the midnight zone. It extends from about 1,000 meters down to around 4,000 meters. In this layer, the absence of sunlight is constant. Day and night no longer exist as separate experiences. The environment is stable and unchanging over short periods of time. There are no daily cycles of light, no shifting shadows, no sunrise, no sunset, only a continuous darkness. Pressure continues to increase as you descend. At 1,000 meters, it is about 100 times greater than at the surface. At 2,000 meters, it reaches around 200 times greater. At 4,000 meters, it approaches 400 times greater. This pressure is consistent and constant. It does not fluctuate. It simply exists. Temperature here is low, typically between 2 and 4 degrees Celsius. It remains stable across large distances. There is no warming from sunlight, no daily variation. The cold is steady and uniform. The water feels dense and still. Movement exists, but it is slow. Currents pass through this zone, but often at low speeds. Sometimes only a few centimeters per second. These currents connect distant parts of the ocean over long periods of time. Without sunlight, photosynthesis cannot occur. This means that energy must come from other sources. One major source is organic material falling from above. This material is often called marine snow. It consists of small particles, including dead plankton, waste, and fragments of organisms. These particles drift slowly downward, providing a continuous but limited supply of energy. As you drift through the darkness, the water appears empty at first. But slowly, small points of light begin to appear. Brief, controlled, and often isolated. These are bioluminescent signals. In the absence of sunlight, bioluminescence becomes one of the primary sources of visible light. Many organisms in this zone can produce light using chemical reactions within their bodies. The light is often blue, sometimes green, because these wavelengths travel most effectively through seawater. The use of light here is controlled. It is not constant, but activated when needed. Some organisms produce flashes to startle predators. Others produce steady glows to attract prey. Some use light to communicate or to recognize members of their own species. Vision still exists in this zone, but it is adapted to darkness. Many organisms have large eyes, sensitive to small amounts of light. Others have reduced eyes or rely on different senses. Some detect pressure changes or chemical signals in the water. These senses help them navigate and find food. Movement in this zone is often slow. Energy is limited, so efficiency is important. Many organisms have soft bodies with minimal skeletal structure. This reduces energy cost and helps them withstand pressure. Some drift, using neutral buoyancy. Others move in short, controlled motions. Predation still occurs, but it is less frequent and often more deliberate. Encounters between organisms are less common due to the vast space. When encounters do happen, they are usually brief and efficient. The scale of this zone is difficult to sense. It extends for thousands of meters, with no visible boundaries, no landmarks, only open water and depth. Sound continues to travel through this space. It moves efficiently and over long distances. Some sounds from above, such as distant waves or marine life, may still pass through, but they are faint and infrequent. Over time, the environment feels consistent. There are no sudden changes, only gradual differences with depth. The darkness remains constant, the temperature stable, the pressure unchanging. As you drift deeper, the sense of direction becomes less meaningful. There is no visual reference for up or down, only a slow awareness of descent. Life continues here, in quiet, measured ways. Each organism is adapted to conserve energy, to function in darkness, and to survive under pressure. The midnight zone is not empty. It is simply sparse, a place where distance separates life, and time moves slowly. And as you continue to drift downward, the water begins to feel even more still, as the open expanse gradually gives way to a distant, unseen ocean floor below. You are now descending beyond 4,000 meters. The water around you is completely dark. The midnight zone has ended. You have entered the abyssal-pelagic zone, often called the abyssal zone. It extends from about 4,000 meters down to approximately 6,000 meters. Here, sunlight is entirely absent. There is no hint of natural light, not from the surface, not from any other source. Pressure is extreme. At 4,000 meters, it is about 400 times greater than at the surface. At 6,000 meters, it reaches roughly 600 times surface pressure. The force is constant and unyielding. Temperature is cold, typically around 2 degrees Celsius. It varies little with depth. There are no daily fluctuations. The water is stable, dense, and still. Currents exist, but they are very slow. Only a few centimeters per second. The vast space is quiet and empty-looking. Yet life persists, though it is sparse. Organisms in this zone are highly specialized. Many have soft bodies with minimal skeletal structures. This helps them conserve energy and survive under immense pressure. Some are small, others are elongated. All are adapted to this extreme environment. Bioluminescence remains important. Many species produce light to attract prey, to communicate, or to avoid predators. The light is mostly blue or green, because these colors travel farthest in water. Energy is scarce. Most food comes from marine snow. Particles slowly drift down from the layers above. Dead organisms, waste, and organic fragments provide nutrients. This supply is limited and unpredictable. Because of this, organisms move slowly, conserving energy. Most swimming is deliberate, short bursts, rather than constant motion. Predators exist, but encounters are rare. The vast distances separate individuals and reduce competition. Many species rely on ambush strategies, waiting patiently for prey. Some detect movement through vibrations in the water. Others sense chemical cues. Vision is limited to detecting faint bioluminescence. Large eyes are common, capturing the smallest amounts of light. The abyssal-pelagic zone is vast, stretching across the deep ocean floor. There are no visible reference points, only open water and extreme depth. Sound travels efficiently, but is sparse. Sources are limited. Most noise comes from movement of organisms or distant tectonic activity. The seafloor begins to approach, slowly descending as you go deeper. Sediment and rocks form the abyssal plains, mostly flat and wide. Occasional ridges or seamounts rise, creating structure and habitat for specialized life. Hydrothermal vents are also present in some regions. They release hot, mineral-rich water into the cold abyss, supporting unique ecosystems entirely independent of sunlight. Microorganisms convert chemical energy into food, forming the base of the local food chain. Life around these vents is concentrated. Unlike the sparse surrounding water, species grow larger and more numerous. These communities are isolated and rely on chemical energy rather than sunlight. Adaptations in this zone are extreme. Many fish have expandable stomachs to take advantage of any food encountered. Others have long jaws or hinged teeth to catch prey in darkness. Some have flabby bodies, minimal muscle, and low metabolic rates. Reproduction is often slow, with fewer offspring. Because survival is uncertain, energy is allocated carefully. Many species produce eggs that float upward for part of development before returning to the deep. As you drift, the environment remains uniform. The water is dark, cold, and under constant pressure. Life exists quietly, moving deliberately. Each organism adapted to scarcity and darkness. The abyssal zone is not lifeless. It is simply extreme, sparse, and highly specialized. The rules of survival here are strict. As you continue downward, the water becomes even denser. The floor approaches slowly, unseen, vast. You are now entering the hadal-pelagic zone, often called the hadal zone. This is the deepest part of the ocean, extending from approximately 6,000 meters to nearly 11,000 meters. Here, conditions are extreme. Pressure reaches levels unimaginable at the surface. At 6,000 meters, pressure is about 600 times that at sea level. At the deepest trenches, it can exceed 1,100 times surface pressure. The water is completely dark. No sunlight penetrates to this depth. Not even a faint blue glow remains. Temperature is near freezing, typically between 1 and 2 degrees Celsius. This temperature remains steady across long distances. Currents are extremely slow, only centimeters per second, creating a stable but dense environment. Life here is sparse, yet present. Organisms have evolved extraordinary adaptations. Many have soft, flexible bodies to withstand immense pressure. Skeletons are minimal or absent. Muscles are reduced, conserving energy. Energy itself is scarce. Most food comes from marine snow, dead plankton, fragments of organisms, and other particles slowly drift down from the upper zones. Food arrives unpredictably, in small quantities. Organisms often have expandable stomachs to make the most of every opportunity. Some are opportunistic feeders. Others specialize in scavenging. Bioluminescence is still used, though less common than in shallower zones. Many organisms rely on chemical sensing or tactile detection to locate food. Some detect vibrations or changes in water pressure. Others use chemoreception, sensing dissolved chemicals. Reproduction in the hadal zone is slow. Many species produce few eggs, each with a higher chance of survival. Some species' larvae rise toward upper zones for development before returning to the depths. Predators exist, but interactions are rare. The vastness separates organisms. Many employ sit-and-wait strategies, conserving energy. Others move slowly, deliberately. Hydrothermal vents and cold seeps are present. Though less frequent than in the abyssal zone, they support localized communities, entirely independent of sunlight. Microbes convert chemical energy into food, forming the base of these isolated ecosystems. The seafloor in hadal trenches is often steep, with deep canyon-like structures and rugged terrain. Sediment accumulates slowly, covering rock surfaces. Small organisms burrow into it. Life here is adapted to both pressure and scarcity. Organisms are resilient, slow-moving, and efficient. Vision is limited or absent. Some species have reduced eyes. Others rely entirely on senses other than sight. Detecting vibrations, chemical signals, or water movement. Bioluminescence is used sparingly, mostly for attracting prey or communication over short distances. Light is brief, controlled, and highly efficient. Sound travels efficiently in these depths. Though sources are rare, some species produce low-frequency sounds to communicate or detect others over long distances. But encounters are still infrequent. Pressure, darkness, and cold define this zone. The environment is stable, with very slow change. Currents exist, but movement is minimal. Life adapts. The hadal zone is extreme, and yet life persists. Quietly, deliberately. Each organism is uniquely suited to survive in darkness and under pressure, conserving energy and using food efficiently. As you drift along the deepest parts of the ocean, you are surrounded by silence, darkness, and immense pressure. The hadal zone stretches below you, vast and largely unexplored. You are now beginning to rise from the deepest trenches. The hadal zone gradually ends, and the abyssal zone returns. Pressure decreases slowly, though it remains extreme. Temperature remains near freezing, and darkness continues. Life is sparse and highly adapted. The patterns you observed in the hadal zone continue here. Organisms are mostly small, soft-bodied, and slow-moving, conserving energy. Food is limited, primarily arriving as marine snow or occasional carcasses from above. Bioluminescence remains a key adaptation. Some species produce steady glows. Others flash light briefly. The light is mostly blue or green, traveling efficiently through water. Vision is adapted to dim light. Eyes are large in some species, reduced in others. Some rely on chemical and tactile senses. Reproduction is slow, with few offspring. Larvae of some species drift upward for development, before returning to the depths. Predation is deliberate. Encounters are rare. Organisms often wait patiently for prey. The seafloor is mostly flat, forming abyssal plains. Occasional seamounts or ridges rise, providing structure and habitat. Hydrothermal vents appear sporadically, supporting communities independent of sunlight. Currents exist, but are slow. Only a few centimeters per second. Movement of water is gradual, transporting nutrients across long distances. Sound travels efficiently. Though sources are rare, low-frequency sounds help organisms detect movement and communicate over distance. Pressure, temperature, and darkness create a stable environment. Life adapts. Energy is conserved. Every organism functions within strict limits. Organic matter from above fuels life, slowly drifting down. Some animals have expandable stomachs, taking advantage of scarce opportunities. Others specialize in scavenging. Movement is measured. Energy is used efficiently. Bodies are soft. Skeletal structures minimal. Metabolism is slow. Bioluminescence guides interactions. Flashes startle predators. Steady glows attract prey. Some species communicate with light. The vastness separates individuals, reducing competition. Encounters are brief and efficient. Adaptations are extreme. Life in the abyssal zone is sparse, quiet, and deliberate. Each organism suited to darkness, pressure, and limited energy. As you continue to rise slowly, the first faint hints of light from the mesopelagic zone appear above. Blue fades to dim green, and bioluminescent flashes become more frequent. Pressure gradually decreases. Water becomes less dense, and life becomes slightly more abundant. You are now rising into the mesopelagic zone, often called the twilight zone. It extends roughly from 200 meters to 1,000 meters below the surface. Sunlight is faint here, not bright enough for photosynthesis, but enough to create a dim bluish glow. Pressure decreases compared to the abyssal and hadal zones, though still higher than at the surface, gradually reducing as you ascend. Temperature begins to increase, ranging from near 4 degrees Celsius at the bottom to about 8 or 10 degrees Celsius near the top. Water here is more dynamic. Currents are stronger than in the deep zones. Movement is gentle, but persistent. Organic material from the surface reaches this zone more abundantly. Particles drift downward and provide a source of energy for life below. Small animals feed on marine snow, while larger predators hunt these smaller creatures. Bioluminescence is widespread. Many species have light-producing organs to attract prey. Some use it to communicate, others to confuse predators. Light is mostly blue or green, as these wavelengths travel farthest through water. Vision is adapted to low light. Many species have large eyes, highly sensitive to faint light. Some use tubular eyes to maximize light capture. Others rely on lateral line systems to detect movement in water. Vertical migration is a common behavior. Many animals rise toward the surface at night to feed, then descend again during the day. This daily movement allows them to avoid predators and access food efficiently. Predators are present, but encounters are intermittent. Fish such as lanternfish are abundant, along with squid and other small organisms. They form dense layers in the water column, providing prey for larger animals. Reproduction is more active than in deeper zones. Many species produce numerous eggs, which develop in this zone. Some larvae drift upward into sunlit waters before returning as juveniles. Temperature gradients create stratification. Warmer water near the surface, cooler water below. This layer of gradual change is called the thermocline. Oxygen levels are higher than in the abyssal zone, but lower than at the surface. Many species have adaptations to conserve oxygen. Slow metabolism and efficient gills help sustain life. Sound travels differently here. Some fish produce low-frequency calls. Others produce clicks or short pulses of sound. These help with communication, navigation, and detecting prey. The twilight zone is transitional between the sunlit epipelagic zone above and the dark abyss below. Energy availability increases upward. Currents and temperature gradients create movement. Some nutrients sink downward, supporting deep life. Others are mixed back toward the surface. Predators in this zone are more diverse. Squid, midwater fish, and jellyfish interact with one another. Sometimes in small schools, sometimes solitary. Vertical migration allows survival in a zone with fluctuating food availability. The mesopelagic zone is rich in life compared to deeper layers, but less abundant than the epipelagic zone. Species are adapted for both scarcity and occasional abundance. Bioluminescence becomes more noticeable. Points of light flicker and drift, creating subtle patterns in the water. These signals help organize interactions. Life here is still cautious. Energy efficiency remains key. Movement is deliberate, and predation strategies are precise. This zone forms a connection between the surface and the deep ocean. It transports energy downward and sustains deep-sea life. Seasonal variations from surface productivity affect this zone. Many species migrate vertically to exploit changes in food availability. Others remain at steady depths, conserving energy. The twilight zone is vast, stretching across all oceans and linking different habitats. It is less explored than the surface. Yet it plays a crucial role in the ocean's ecosystem, cycling nutrients, sustaining life, and supporting the food web. Organisms here are adapted for both light and darkness. Energy is intermittent, and opportunities must be used efficiently. Many species are small and numerous, forming dense midwater communities. Others are larger and more solitary. Reproductive strategies vary. Some release eggs freely. Others guard their young or use brooding. Adaptation is continuous. As you drift upward, light increases. The faint blue glow gradually strengthens, and the epipelagic zone approaches. Nutrient availability rises, and life becomes denser. You can sense the transition. You are now entering the epipelagic zone, often called the sunlight zone. It extends from the surface down to approximately 200 meters. Sunlight penetrates fully here, allowing photosynthesis. This zone is warm. Temperatures vary with location and season. Currents are active, mixing water and distributing nutrients. Life is abundant. Phytoplankton form the base of the food web. They convert sunlight into energy. Zooplankton feed on phytoplankton. Small fish feed on zooplankton. Larger fish and predators feed on smaller fish. This creates a dynamic ecosystem. Interactions are frequent, and energy moves quickly through the food chain. Schools of fish move in synchronized patterns, avoiding predators and seeking food. Birds, marine mammals, and humans interact with this zone, feeding, hunting, and navigating through it. Epipelagic waters are influenced by sunlight, which drives daily and seasonal cycles. Phytoplankton bloom when nutrients and light are sufficient, supporting higher trophic levels. During these blooms, fish populations expand, and predators take advantage. Vertical mixing of water distributes oxygen and nutrients, supporting continuous life. Waves and surface currents create turbulence, affecting small organisms and helping them stay suspended in water. Temperature differences drive seasonal stratification, forming layers of water. Warm water above, cooler water below. The epipelagic zone is highly productive. Energy is abundant, and organisms are numerous. Phytoplankton are eaten by zooplankton, which are eaten by small fish, and then by larger fish or marine mammals. Predation is frequent, but so is reproduction. Many species release eggs into the water. Some guard their young, while others allow dispersal. Diversity is high. Birds, fish, and mammals use the zone extensively. Dolphins, whales, and seabirds hunt here. Humans fish commercially and rely on its resources. Currents transport nutrients and plankton over long distances, connecting distant regions and creating seasonal patterns. Upwelling brings nutrient-rich water from deeper layers, supporting blooms and feeding cycles. Epipelagic life is adapted to light and warmth. Many fish are streamlined, fast swimmers, avoiding predators. Some use camouflage or schooling to survive. Reproduction strategies vary. Some species are broadcast spawners. Others build nests or protect young. Seasonal migrations occur. Vertical movement connects epipelagic species with deeper zones. Many mesopelagic species rise at night, feeding near the surface, and returning to the twilight zone during the day. The epipelagic zone influences global climate. Sunlight drives heat distribution, and surface currents affect ocean circulation. Nutrient cycles here impact carbon storage. Photosynthesis removes carbon dioxide from the atmosphere, supporting life across ocean layers. Dead material sinks downward, feeding life in mesopelagic, abyssal, and hadal zones. Human activity affects this zone. Overfishing alters populations. Pollution introduces chemicals and plastics. These impacts propagate through the food web. Climate change modifies temperature, currents, and productivity, affecting species distribution and ecosystem balance. Despite challenges, the epipelagic zone remains the most vibrant layer of the ocean, full of light, life, and movement, connecting all other zones below. It provides energy, food, and oxygen, sustaining the entire marine ecosystem. As you drift toward the surface, light increases fully. Colors become visible, and life is abundant. The surface shimmers with activity. You are now approaching the ocean surface. The epipelagic zone ends, and you enter the interface with air and water. Sunlight is strong, illuminating the water fully. Waves ripple gently, and currents flow with energy. This is the layer most influenced by weather and wind. Temperature is highest here. Warmth varies with latitude and season. Sunlight warms the surface, while deeper layers remain cooler. Life is abundant. Phytoplankton bloom near the surface, converting sunlight into energy. Zooplankton feed on phytoplankton. Small fish feed on zooplankton, and larger predators hunt these fish. Birds such as gulls and terns skim the surface, diving occasionally to catch fish. Marine mammals, including dolphins and whales, feed actively. Humans interact frequently, fishing, sailing, and observing life. The surface zone is dynamic. Waves, tides, and wind create constant movement. Currents mix water, distributing heat and nutrients. Reproduction is active here. Many species release eggs at the surface. Larvae develop in sunlit waters. Predators are abundant, and hunting is frequent. Vertical migration connects surface waters with deeper zones. Many mesopelagic species rise at night, feeding near the surface, before returning to the twilight zone. Nutrient cycles are rapid. Photosynthesis provides oxygen, supporting aerobic life. Dead material sinks downward, feeding deeper zones. The surface interacts directly with the atmosphere. Carbon dioxide exchange occurs here. Heat is transferred from sunlight to water, driving weather patterns and climate. Human activity significantly affects this layer. Pollution, overfishing, and climate change introduce changes. Plastics, chemicals, and noise disturb ecosystems. Conservation efforts aim to mitigate these impacts. The surface zone connects all ocean layers, from sunlight above to the hadal depths below. Energy flows downward, sustaining life throughout. Seasonal changes influence surface productivity. Temperature shifts and nutrient availability drive phytoplankton blooms. Feeding cycles respond accordingly. Predators adjust their hunting patterns. Winds, storms, and tides create turbulence, dispersing nutrients and organisms, maintaining ecological balance. Epipelagic and surface interactions are continuous. Fish, mammals, and birds exploit resources actively. Some migrate seasonally. Others stay in localized areas. Life strategies vary, but energy efficiency remains essential. Bioluminescence fades here. Sunlight dominates. Yet some surface species retain subtle light displays. They use it for mating or communication. Surface water chemistry is influenced by rainfall and river input. Salinity fluctuates. Nutrients from land enter the ocean, supporting blooms and surface life. Oxygen levels are highest near the surface, supporting diverse aerobic life. Depth gradients lower oxygen farther below. Surface currents redistribute heat globally. Climate patterns such as El Niño and La Niña originate here, affecting temperature, winds, and precipitation worldwide. Seasonal mixing of surface and deeper waters regulates nutrient cycles, ensuring long-term ecosystem stability. The surface zone is the most visible part of the ocean. Life is abundant, energy is high, and movement is constant. It is the gateway to all deeper layers. Sunlight, warmth, and nutrients support life below, connecting epipelagic, mesopelagic, abyssal, and hadal zones. Humans rely on this zone for food, transport, and climate regulation. As you observe the ocean from above, waves shimmer. Light penetrates downward, and the entire water column hums with life. You are now reflecting on the ocean as a complete system. From surface to hadal depths, every zone connects with others. Energy flows downward from sunlight, and nutrients move throughout. Life adapts to its environment. The surface is dynamic. Sunlight warms water and drives productivity. Currents and waves mix nutrients, supporting phytoplankton blooms. Zooplankton feed on these blooms. Small fish feed on zooplankton, and larger predators follow. Vertical migration links epipelagic and mesopelagic zones. Many species rise at night, feeding near the surface, and returning to the twilight zone by day. The mesopelagic zone is a transitional layer. Light fades, pressure increases, and energy becomes scarcer. Bioluminescence dominates, guiding communication, hunting, and avoidance. Reproduction is active. Abyssal zones are stable, dark, and cold. Pressure is extreme, and life is sparse. Organisms move slowly, conserving energy. They feed on marine snow. Occasionally, scavengers consume larger carcasses. Hydrothermal vents create localized ecosystems, independent of sunlight. Organisms rely on chemosynthesis. The hadal zone reaches the deepest trenches. Pressure is immense, and temperature is near freezing. Life is rare but highly specialized. Each organism is adapted for survival in extreme conditions. Food is limited, and energy must be conserved. Bioluminescence is less common. Movement is deliberate, and encounters are infrequent. Organisms are often soft-bodied. Ascent toward shallower waters gradually decreases pressure. Temperature rises slowly, and light begins to appear in the mesopelagic zone. Life becomes more abundant and interactions more frequent. Predators and prey adjust to changing conditions. Energy availability increases, and vertical migration continues. Bioluminescence is more pronounced here. Rising further into the epipelagic zone, sunlight is strong. Photosynthesis supports dense life. Schools of fish, mammals, and birds exploit the resources. Surface waters are influenced by weather, currents, and human activity. Temperature, salinity, and nutrients fluctuate, supporting a complex ecosystem. Overfishing, pollution, and climate change impact this zone. Nutrient cycles link surface and deep zones. Dead material sinks downward, feeding mesopelagic, abyssal, and hadal communities. Energy flows connect the entire ocean vertically. Oxygen is produced at the surface and distributed downward, supporting aerobic life throughout. Currents and mixing regulate nutrients and temperature. Seasonal and geographic changes affect each zone. Productivity, reproduction, and migration adjust accordingly. Many species migrate vertically or horizontally, responding to food availability and environmental conditions. Life strategies vary, from rapid reproduction near the surface to energy conservation in the deep ocean. Movement, feeding, and survival are calibrated precisely. Bioluminescence guides activity in the twilight and deep zones. Sunlight dominates near the surface, but energy still reaches the deepest layers. Nutrients, organic matter, and energy flow downward. The ocean is a continuous system, each layer supporting the next, and depending on energy from above. Life is interconnected. Reproduction, feeding, movement, and communication occur throughout. Pressure, temperature, and light define adaptations. Energy is used efficiently, and survival strategies are precise. Human activity affects all zones. Conservation and management are essential. Maintaining ecosystem health ensures stability and resilience across depths. The ocean is vast, layered, and interconnected. From surface waves to hadal trenches, every zone has unique conditions and specialized life. Together, these layers form a complete system, sustaining life, cycling energy, and connecting all forms of oceanic existence. You are now considering the ocean as a whole, a vast and interconnected system. From the surface, sunlight penetrates only the top layers, supporting photosynthesis. Phytoplankton convert light into energy. Zooplankton feed on phytoplankton. Small fish consume zooplankton, and larger predators follow. Energy moves upward while matter cycles downward. The epipelagic zone is the most active. Currents mix nutrients. Waves stir the water, and temperature fluctuates. Birds skim the surface. Dolphins hunt near the top, and humans fish extensively. Vertical migration connects epipelagic and mesopelagic species. Many organisms rise at night to feed, returning to twilight depths by day. Bioluminescence begins to appear, guiding hunting, communication, and avoidance. The mesopelagic zone is dimly lit. Pressure increases steadily, temperature drops, and energy becomes more limited. Organisms here conserve energy, using slow movements and minimal activity. Bioluminescence is frequent, helping predators find prey and individuals signal mates. The abyssal zone is dark, cold, and stable. Pressure is extreme, and food is scarce. Life exists mostly on marine snow or occasional carcasses sinking from above. Hydrothermal vents create local hotspots, supporting chemosynthetic life independent of sunlight. The hadal zone occupies the deepest trenches. Pressure is immense, temperature near freezing, and life is rare but highly adapted. Organisms here are soft-bodied, conserving energy and withstanding extreme pressure. Vertical and horizontal energy flows connect zones. Nutrients, oxygen, and organic matter move between layers, sustaining life from surface to trench. Seasonal changes affect surface productivity. Phytoplankton blooms respond to sunlight, temperature, and nutrients. Zooplankton feed on blooms. Fish consume zooplankton, and larger predators follow. Reproduction strategies vary. Some species spawn at the surface. Others guard their young in mesopelagic depths. Deep-sea species reproduce slowly. Adaptations to pressure, darkness, and low energy are essential. Movement is deliberate. Predation is infrequent. And survival depends on efficiency. Bioluminescence is critical in twilight and deeper zones. Light is used for hunting, mating, and camouflage. Sunlight dominates epipelagic layers. But energy from surface productivity reaches abyssal and hadal zones. Oxygen is produced near the surface and transported downward by currents and mixing, supporting aerobic life throughout the ocean. Nutrient cycling is continuous. Dead material and excretions sink, feeding deeper layers, while vertical migration redistributes energy upward. Currents regulate temperature, nutrients, and oxygen. Climate, weather, and seasonal shifts influence every zone. Productivity rises and falls. Migrations adjust. And reproduction follows environmental cues. Human activity affects all zones. Overfishing, pollution, and climate change alter energy flow and species distribution. Conservation and sustainable management are essential. Maintaining ecosystem balance preserves connectivity across depths. The ocean is a continuous, layered system. Each layer depends on the others. Life is interconnected. From sunlight-driven surface zones to nutrient-dependent hadal trenches. Adaptation, energy efficiency, and survival strategies define organisms at every depth. Movement, feeding, reproduction, and communication are carefully balanced. Pressure, temperature, and light shape life. And energy moves both downward and upward. Humans interact with the ocean surface, but must respect deeper zones. Conserving resources ensures resilience and continuity. The ocean is vast, complex, and interconnected. From shimmering surface waters to the silent, cold depths, every zone supports life and contributes to global ecological balance.